we introduce Quark, a generalizable network capable of performing high-resolution, novel view synthesis where 3D reconstruction and rendering of novel viewpoints are computed simultaneously and at real-time frame rates. Our method takes as input a collection of sparse, color images, or video streams. These inputs can either be structured, as from a camera rig, or from unstructured captures, including large datasets with hundreds of images that are typically processed with expensive offline methods. In contrast to these methods, Quark performs live image-based rendering on demand and interactively by selecting appropriate nearby input views. Our approach combines 3D reconstruction and rendering into a single network that is trained ahead of time on real-world scenes. Once trained, our network can generalize across a wide range of novel scenes, and a single network evaluation runs in just 33 milliseconds. This fast evaluation time is partially enabled by the network's internal representation of the 3D scene as a stack of layered depth maps that conform to the geometry of the scene. The network learns to directly output depth layers with associated density and blend weight properties that allow us to perform layer-wise, image-based rendering using the original input images. This results in high-quality, high-resolution images without holes or gaps. In order to solve the layered depth map for each frame, we designed a novel feed-forward neural network that encodes and downsamples input images, and then performs a multi-scale render and refine algorithm to progressively refine and upsample the layered depth map. The network ultimately produces high-resolution depth, density, and blend weights. The original input images are projected onto depth, blended using blend weights, and then the resulting layers are over-composited to produce the final image. See our paper for an in-depth description of the algorithm. Our method offers quality that approaches the state-of-the-art offline methods like GPNR, even though it is multiple orders of magnitude faster and capable of rendering at significantly higher resolution. Feed-forward eNRF can reconstruct and render at interactive rates, but our method is still 6 to 8 times faster and shows significantly higher quality. Here we compare to Simply because they use layered meshes, which are similar to layered depth maps, and a render and refine network structure. Our novel network architecture produces higher quality while being 1,000 times faster. And for a modest drop in frame rate from 30 FPS to 10 FPS, we show that it is possible to tune our Quark Plus algorithm for even higher quality. Our method can capture complex geometry and can render thin structures even when these are layered across different depths. While our representation does not explicitly encode complex material properties, the combination of layers, alpha densities, and blend weights offer a surprising amount of flexibility to capture the appearance of shiny materials and even refractive objects. Our method can even render scenes with full 360 orbits that normally require expensive offline optimization like NeRF and 3D Gaussian splatting. And because our method runs in real time and reconstructs a new layered depth map for each video frame, it is possible to perform novel view synthesis in real time on video datasets. However, artifacts are visible on the perimeter of some examples. This is because our view selection algorithm sometimes fails to find views that provide full coverage of the novel view. Suboptimal camera coverage can also lead to temporal inconsistencies in some portions of the scene. And because our method strictly relies on forming the final image via blended combination of the input images, it can be prone to artifacts arising from input image differences in exposure, color, or vignetting. But overall, our method generalizes well to a variety of scenes, even from datasets that were not seen during training. Scenes with moving content work just as well as static scenes, and most natural scene content is reconstructed very well, including scenes with complex objects and lighting, transparent objects, plants, people, animals with shaggy hair, and atmospheric effects like fire and sparks. In summary, our method shows high-quality view synthesis at interactive rates is possible, which may lead to exciting new applications.